I think we're in for a really a rare treat this evening. If you've been involved in amateur astronomy, especially here in Texas, for any length of time, you probably already are familiar with who Robert Reeves is. I can tell you, Robert's been doing amateur astronomy for almost as long as some of us have been around. But at any rate, I'll get to that in a minute. Um, Robert is a longtime supporter of amateur astronomy. He's become very renowned in the community. He's the author of seven books that he's done uh, uh, on the moon, on astrophotography, on space exploration, and Robert has agreed to share with us his favorite places on the moon. He's going to show us how he observes the moon. He's going to show us some of his favorite places, as well as give us a lot of tips on how to observe. So I hope you all will benefit from this. I can tell you, most of us, especially astrophotographers, kind of got in the frame of mind when there's a moon out, we don't do astronomy. Listen to if you listen to Robert for any length of time, I guarantee you'll be out observing the moon. With that, I'll turn it over to Robert.
Well, thank you very much. Many of my long-term Houston friends are aware of the family medical issues that are keeping me pretty close to the barn nowadays. But otherwise, I would have been thrilled to come over to Houston and give this in person if y'all still have live meetings. But things have changed a little bit here. I've had to drop out of my activities with the Texas Star Party and various other things, but I'm extremely grateful for the ability to speak to you all via Zoom like we are now. It keeps me alive in this business and keeps my heart going in this. So I appreciate it very much. Now, Don mentioned that I had written a number of books about the moon, so I'll do the 10-penny commercial first before we dive into the program. In August of 2023, I came out with a book, Exploring the Moon with Robert Reeves. Note my name is very pretentiously in the title to separate this book from the other dozen books out there also titled Exploring the Moon. This is available on Amazon. And last September, Firefly Books released my newest one, Photographic Atlas of the Moon. And in this one, I am personally astonished at the image quality that Firefly puts into these books. I can tell no difference between the pictures in this book and the ones that come off of my Canon wide format printer. So it's exquisite. Exploring the Moon with Robert Reeves explains the moon to you. The Photographic Atlas of the Moon by Robert Reeves will show you the moon. They are complementary books. They don't overlap an enormous amount. But how you would approach the moon is up to you. Both of them available on Amazon. So, as Don says, I've been an astronomer for a long time, 65 years, as a matter of fact. Yes, I am that old. I'm almost 80. 80 going on about 35. I've evolved into being an author, lecturer, and I also work for the Celestron Telescope Company. So keep my finger in the pie. And I enjoy it very much. The moon has become one of my passions over my lifetime, and I like to share it with others. So let's move along here and mention that if you get Astronomy Magazine, or if you go on the Astronomy Magazine website, please take a look at the website astronomy.com now, because they have two of my articles about the moon on it. This one came out just this morning. The middle-aged moon had a magnetic field. I've done a series of articles for them, reviewing the results from various moon missions from India, China, and so forth, and amazing amount of research coming out of there. Middle-aged moon had a magnetic field, like I said, released this morning. The the January issue, whoops, don't mean to do that. The January issue of Astronomy had the cover article about how Artemis will return us to the moon. You open it up and you'll find that somebody else's name is on that article. Astronomy admitted that for the first time in the magazine's existence, they really screwed up. They put somebody else's name on my article. But the website now has that article, a majority of it. Some of the graphics are gone, but that article is now online at astronomy.com, how Artemis will land humans on the moon. So if you don't get the magazine, you can still see this article at astronomy.com. So moving on, whoops, there's the cover picture that is on the January issue of Astronomy. But moving on, my presentation, Postcards from the Moon. I take the title from the frequent images that I put up on Facebook that I call Postcards from the Moon, where I relay a little bit of information about the area, the significance of it, how it relates to me sometimes, and have a lot of fun with it. But basically, this program is an iteration of a program I gave to the Chinese Academy of Sciences in Beijing back in 2019. So I've gotten a lot of mileage out of this program, and I hope you enjoy it too. So, in the half century since Apollo, much has appeared in the media about how we got to the moon, the politics of why we went to the moon, and the personalities that engineered, directed, and flew the Apollo missions to the moon. But in the half century since humans last set foot on the moon, how much does the average person actually know about the moon? Well, it's surprisingly little, and I've made it my mission to try to rectify that. So, I've been in love with the moon my entire life. My earliest memories of the moon were watching moonrise through my bedroom window when I was a child. Today, space age explorations have not stripped the wonder and the mystery that I felt for the moon when I was young. There's an actual name for people like me, and before you even think lunatic, I'm going to stop you right there. There is a word called selenophile, a person who loves the moon. And after you become acquainted with the moon, I hope you too will become a selenophile. Now, over the past 20 years, I have spent a large amount of time chasing big telescopes across the southern United States in order to take high-resolution lunar photographs. Well, the irony of it is, I find that I can take better images of the moon from my own observatory in my backyard with 7 to 11-inch telescopes because the poor seeing common around here does not degrade the image in smaller telescopes as much as it does in larger telescopes. So, how good is modern lunar imaging with a modest amateur telescope? Well, the image on the right is a plate from the famous Kuiper Lunar Atlas. Back in the early 60s, as they were preparing for Apollo before the lunar orbiter missions, this was the best the professional astronomers could do from the Earth. Now, the image on the left, taken from my backyard with the Celestron 11 telescope. The two fields are the same, except the Kuiper is upside down because prior to 1960, the convention was to print images of the moon south up. Nowadays, we print them like a terrestrial map, north up. But I'll let you be the judge as to how good our backyard photography of the moon is nowadays. So I like to say that I have no special talent. I'm only passionately curious, just like you are. Otherwise, you wouldn't be here listening to me. So I hope a little bit of my enthusiasm for the moon will rub off on you. So the moon is a world that shows us a scene that is rugged yet serene, harsh yet beautiful, alien yet appealing, tortured yet it's calm, and strange yet friendly. So the moon is my playground, and I invite you to come out and play with me. So when I was young, the moon was a big deal. This is back when Apollo was ramping up. The space program was just beginning. The moon at that time was still a dream. a goal, a destination, a place of mystery to be explored by brave heroes who dared to ride a pillar of fire and set foot on another world. Then in the mid-1970s, there was a fundamental shift in amateur astronomy. The introduction of the 8-instrument Cassegrain gave us a powerful, affordable, portable telescope that opened up the deep sky to amateurs. The moon then kind of faded from amateur astronomy. Well, my goal in this presentation is twofold: to bring the moon back within our astronomical realm, to make it not something to be avoided because it interferes with the deep sky, but to get you not to just look at the moon, but to see it and understand it. Now, today, amateur astronomers consider the moon boring, a place covered with bumps and holes. But the moon is not visually static. The moon is a geologic wonderland. It changes day by day, even hour by hour. There's much to see on the moon once you know what to look for. And I want you to go back to the moon with me and rediscover its wonders. So tonight we're going to look at the creation of the moon, the evolution of the moon's face, understand the various forms of lunar geology, and then explore some sentimental lunar favorites. Now, a summary of our understanding of the physical moon over the past 50 years since the space age explorations began. The moon is not the primordial object we thought it was before the space age. The moon is made of rocky material that has been melted and heavily modified by both exogenic and endogenic forces. Now, those are fancy words for saying external and internal forces, that is, meteor and asteroid impacts or internal volcanism. Now, two conclusions were drawn about the moon prior to the space age. The moon underwent a huge bombardment about 50 million years after it formed, and volcanic activity began about 700 million years after the moon formed and was prevalent for about 1 billion years. Of course, now research is showing that period of volcanism extended almost up to the modern era. So our understanding of the moon continues to evolve. So over the past 50 years of intense research, the moon remains lifeless. In the lunar samples that have been returned to Earth, no living organisms, fossils, or organic compounds have been found. The lunar evolution process, through the accretion of smaller bodies, melting, and impacts, have left the moon with a crust about 60 kilometers deep and a uniform lithosphere reaching a depth of about 1,000 kilometers. Below this lies a partially liquid core, and we still do not know for sure if the moon possesses a small iron core, but I am betting that it does. Now, the oldest rocks on the moon are the 4.6 billion year old light-colored highlands known as the terrae. The youngest rocks on the moon are the 3.2 billion year old maria formed by volcanic eruptions. Thus, the youngest rocks on the moon are about as old as the oldest rocks that we have found on the Earth. The Earth and moon formed from the same source material. The Earth and moon evolved similarly, but the moon is depleted in iron and volatile elements. Lunar rocks formed in high-temperature events with little chemical reaction with water. Evidence of the earliest events that formed both the Earth and the moon are now only seen on the moon. And I can expand that statement to say that similarly, Mercury, Venus, and Mars experienced the same impact cratering that both the Earth and the moon did. But telescopically from our backyard, we only see the moon. The other planets are too far away to resolve the impact details. So, lunar rocks can be broadly categorized into three types: volcanic basalts that erupted from the interior and formed the maria, anorthosites that are the lightweight material that floated to the surface of an early molten moon, and breccias created by the mixing of other rocks crushed by meteorite impacts. After the molten moon solidified, it was blasted by thousands of asteroid impacts, primarily during the late heavy bombardment, which coincides with what we now call the Nectarian epoch. The largest impacts created the basins that later flooded with lava and formed the maria. The primordial moon was also much closer to the Earth than the modern moon. After its creation, the moon was little more further away from Earth than the current geosynchronous satellites that provide us with communications, weather information, and so forth. So, the crust of the far side of the moon, curiously, is thicker than the near side. Most volcanic flooding of the basins occurred on the thinner crust, what is now the near side. Higher density basalt within the near side basins displace the moon's center of gravity, allowing the moon to enter a synchronous rotation, which always keeps the same face toward Earth. Now, over the billions of years of its existence, the moon has been blasted by countless meteorite impacts that have crushed the upper layer of the crust into a mixture of dust and rock fragments that we call regolith. Because impacts excavate rock samples from deep within the moon's crust, it is possible by selectively choosing the rock samples on the surface, it is possible to analyze the interior of the moon. Now, the earliest event on the moon was necessarily the formation of the moon. There's been many theories proposed on how the moon came into being, but the one that has survived the test of time the longest and passes all the modern tests is the Earth and the moon were created by the collision of a proto-Earth and another Mars-sized object also orbiting the inner solar system almost 4.5 billion years ago. This Mars-sized interloper, we hypothetically call it Theia, and it collided with Earth, shattered both worlds, and repeated computer simulations show that from the shattered debris of both worlds, our current Earth evolved and the moon formed from a ring of debris that was left over. Now, the early molten moon, science fiction visions of this glowing red-hot sphere of rock flying through space may work well with pulp science fiction, but in reality, the early moon, even though it was molten, was probably a very dark body. The outer surface probably had a thin, chilled, solid rock crust that insulated the interior of the molten interior. Iron and heavy radioactive elements sank. Silicates floated to the top of this global magma ocean, and it took millions of years for the moon to solidify. Now, as the moon solidified and evolved over the eons, it has undergone various epochs of time. Now, back when we were kids and we were fascinated with dinosaurs, we learned about the strange sounding names like the Jurassic period and the Triassic and so forth. These periods of geologic time, Cretaceous and so forth, way back millions and billions of years ago. Well, the moon underwent a similar geologic timescale. We consider anything that is pre-Nectarian to have occurred between the formation of the moon and about 3.92 billion years ago. Then the late heavy bombardment happened. Massive asteroid impacts rained down on the moon for about 100 million years. And between 3.85 and 3.92 billion years ago, we call this the Nectarian epoch, followed by about a billion years, a little less than a billion years of the Imbrium epoch, where volcanism began to appear and flooded the basins with basalt. This was the Mare formation period. Followed by about a 2 billion year period, the Aristotelian epoch, the post-Mare cratering occurred, and then finally the modern era of the moon, from about a billion years ago to the present, the Copernican epoch. We can tell any crater on the face of the moon that formed during the Copernican epoch has a ray system on it. Rays fade after about a billion years. So if you see a crater on the moon with a ray structure, we consider it to be a Copernican epoch crater and less than a billion years old. So, looking back in time, back to the Nectarian epoch, the moon looked much different. This is 3.85, 3.92 billion years ago. The crust had solidified, but the crater rate formation rate was perhaps 300 times what it is today. Basically, the solar system had a lot more ammunition to throw at us. And this is when the great basins formed. But there was not yet any Mare forming volcanism. You look at this painting by Don Davis, you can see the big giant impact basins, basically where many of today's Mare are. So direct correlation between these impact basins and the modern Mare that formed the face of the man on the moon. Now, during the Imbrium epoch, extensive volcanism flooded these lower lying basins. There is no Mare formation in basins that are above mean lunar elevation. All of the Mare that we see that create the face of the man on the moon are below mean lunar elevation, which is basically lunar sea level. And then finally, the modern moon, the Copernican epoch, billion years to the present. The young craters still retain their ridge structure, and there's been a significant reduction in the rate of crater formation, which is a good thing, because if the Earth gets blasted just as much as the moon does, and if the impact rate were still very high, life on Earth as we know it would not have evolved. So, we get down to it, there are two basic primary landscape forming processes on the moon: volcanism and impact cratering. Everything we see on the moon was created by those two forces or a combination of them. So let's start off with the large features on the moon, the Mare, also known as the lunar seas, because 400 years ago, when the telescope was first applied to the moon, the observers thought these dark areas were actual watery oceans, but quickly realized that wasn't so. But by convention, we still call them lunar seas. And these are fields of dark basalt deposited by ancient volcanism. Now, the basins on the moon are basically huge craters. The Mare laying within them are basalt deposits from volcanism. The Mare and the basins under them are not the same features. Basins were created by asteroid impacts. The Mare were formed by lava eruptions flooding the basins. And not all the basins contain a Mare. There are 70-something gravitationally detectable or visible basins on the moon, but only about a third of them have basalt in them. So the Mare define the face of the moon and create the caricature of the man on the moon. There are 21 named Mare on the near side of the moon. 11 were named by Giovanni Riccioli in the 17th century. 8 were named in the 19th or early 20th centuries, and 2 of them were named during the space age. You tend to think of the map of the moon as constant and unchanging. But the last Mare on the moon, Mare Insularum, was actually named after I moved into the house I'm living in today. So there are still recent things being named on the moon. Now, the common theme to the Mare, here we see Mare Nectaris, Mare Crisium, Serenitatis, Imbrium. They're all round, they're circular. And the one key thing about this that escaped astronomers for almost 350 years of telescopic observation is these lie in a gigantic crater. The rim of the shoreline of the Mare are the rims of gigantic craters. And the same with Mare Humorum down in the southwestern part of the moon. Now, Oceanus Procellarum is the largest of the lunar Mare. It's the only one named an ocean instead of a sea. And twice as big as Mare Imbrium, but because of our perspective, as we see it from Earth, highly foreshortened along the western limb of the moon, Oceanus Procellarum doesn't even contribute to the caricature of the face of the man on the moon, even though it covers almost 2 million square kilometers, over double the size of Mare Imbrium. And not all basins completely filled with lava flows. In case in point, down in the southeastern limb, Mare Austral wraps around the limb of the moon, extends onto the far side of the moon. We only see half of it from the Earth. And Mare Austral is a collection of basalt-filled craters. Now, why didn't the Austral basin fill with lava like the near side basins? Remember, I said the far side of the moon has a thicker crust. The limb of the moon, the proximity to the far side, the thicker far side, limits or restricts the volcanic eruptions from the interior of the moon. There are almost no mare on the far side of the moon, and near the limb, the eruptions were restricted. So Austral ends up being just this mottled patchwork of lava-filled craters instead of a completely solid mare. And not all mare lie within a single basin. Now, Mare Frigoris, the Sea of Cold, up above the face of the Man in the Moon, spans 1,800 kilometers, but it's only 200 kilometers high in north-south dimension. It may lie in portions of the Procellarum, the Imbrium, and the Serenitatis basins. And Mare Frigoris kind of reminds me of the eyebrows above the Man in the Moon's eyes. Moderate or even binoculars will show this effect. Visually, you don't see Mare Frigoris too well, but just a pair of binoculars will show how Frigoris arcs above Mare Imbrium and Mare Serenitatis and looks like eyebrows above the Man in the Moon's eyes. So, lunar mountains. Feature we easily see in a telescope. Earth's mountains are continuously created by plate tectonics and volcanism and are eroded by Earth's weather and oceans. So lunar mountains are created by a different process. Impacts. Lunar mountain chains are the raised rims of impact basins. Now, there are individual peaks at the center of large craters, many large craters, but the mountain chains, like we see arcing around the illustration, are the raised rim of a basin. Now, lunar mountains have remained unchanged since their formation almost 4 billion years ago, whereas Earth's mountains can be significantly altered by weather, plate tectonics, volcanism, erosion, the oceans, in as little as 100 million years. So what we see on the moon has been preserved, whereas Earth has significantly been altered in that period of time. Now, some of the more popular lunar mountain chains, the Alps up north of Mare Imbrium, easy to find because everybody can spot Plateau crater, the dark, florid, almost featureless crater that looks so out of place compared to other craters. So it attracts our attention. Of course, the Alpine Valley, slashing through it, we see on the right-hand side of the image, a very distinctive gash ripped through, well, not ripped, but collapsed through the Alps mountains. Proceeding around the eastern side of shoreline of Mare Imbrium, we come to the Caucasus Mountains. And now we're beginning to see a familiar trend here. These mountain names on the moon are all named after terrestrial mountain chains, such as the Apennine Mountains, which arc down around the southeastern part of Mare Imbrium. And then we get to the southern part, we find the Carpathian Mountains separating Mare Imbrium from Copernicus crater. Whoops, what happened here? I've lost my image. There we are, back on track. All righty. Now, some mountains on the moon, like the Cordillera Mountains, you can only see them for 1 day per lunar month. Now, the Cordillera Mountains, and I'm going to hope that my cursor is moving on your screen too. You see the Cordilleras here highlighted by the shadows cast behind them. And then a little further up, the Rook Mountains, right along the terminator, and then just breaking into sunrise, an unnamed mountain chain that we call the Inner Rooks, but they really don't have a name. Now, these mountains are actually the outer impact rings around the Oriental Basin, which hugs the western limb of the moon. Now, Why do we only see these for one night per month? This is on the western limb of the moon. For the first 13 days of the lunation, this area is still a shadow. The sun literally has not risen on it. So then on the 13th day of the lunation, yes, we're getting some shadows. We can see the Cordillera highlighted by the shadows behind them. But one day later, full moon, there are no shadows on the moon. The Cordillera and the Rooks disappear because there's no contrast shadow behind them. And then for the rest of the lunation, they're illuminated from a very high angle and remain invisible. So one of the lunar challenges is to see the Cordillera and the Rooks just after sunrise. And some prominent mountain chains on the moon, such as the Western Crisium Basin Impact Ring that cradles Mare Crisium, they don't have a name. There's an enormous amount of territory and features on the moon that are still nameless. So it seems curious, but that's the way it is. And let's talk about a different feature, the types of craters on the moon. Not all craters are just boring holes in the ground. There are variations. And there is a crater main sequence too. We take that term, of course, from stellar astronomy, where we discuss the main sequence of stars as they evolve from young to old, from blue to red. But in the case of craters, it's a smaller sequence. Anything smaller than 16 to 21 kilometers in diameter, the dynamics of the impact that create this will only excavate a simple bowl-shaped crater on the moon. Now, if the impact is larger, higher velocity, more mass, and creates a crater greater than 16 to 21 kilometers in diameter, we have what is called a complex crater. In this case, the shock rebound rises up subsurface rock in the middle of it to create a central peak. The crater walls are so high that they don't have enough strength to support themselves, and they collapse and tumble down into the crater, forming a series of benches and terraces as the material tumbles into the crater. But when we get up to a crater that's 300 kilometers or larger, we no longer call it a crater. It is now classified as a basin. So some examples. Helicon and Leverrier up on northwestern Mare Imbrium look essentially like you took a giant ice cream scoop and just carved a divot out of the moon. One of the most famous of the complex craters, Copernicus. We have a direct overhead view of Copernicus from the Earth. So we see the central mountain peaks that have rebounded up. We see how the walls collapse and tumble down into the crater, forming a series of benches and terraces. And then a basin that did not fill with basalt and become a maria, Bailey, down at the southwestern limb, is a prime example. Bailey was originally classified as a crater. But as our definition evolved, and now anything over 300 kilometers in diameter is classified as a basin, Bailey turns out to be 301 kilometers in diameter, so it got an upgrade. It is now Bailey Basin, but classically on lunar charts, it's still looked at as a crater. So examples of some complex craters. They all feature a central peak, a raised elevated peak in the middle, the collapsed terrace walls, Pythagoras up in the northwest, Moretus down near the South Pole, Geminus up north of Mare Crisium. I mentioned crater rays earlier. Rays are composed of the pulverized glassy material thrown from a crater by the impact explosion that created the crater. Now, crater rays fade after about 1 billion years and are an indication that the parent crater is relatively young. Rays are brightest near the full moon. Crater rays are very efficient at reflecting light back toward the source, the sun. And during full moon, the Earth is aligned directly between the sun and the moon. So we're getting the full reflection. Now there's also variations of rayed craters. Monodirectional rays, such as those extending from Messier and Messier A, and the butterfly pattern, like those extending from Proclus crater, are an indication of a very oblique impact. In this case, less than 5 degrees above the horizon, a very slanted impact. And in this case, no ray material splashes in the direction that the impactor came from. Now, first thing somebody's going to, who's not familiar with the moon, is going to say it's such an extreme slant impact. Why didn't it create an elongated crater? Well, it's not the impact that creates the round crater. It is the instantaneous vaporization of the projectile when it slams into the moon at cosmic speeds that liberates huge amounts of kinetic energy that essentially acts like a bomb and creates a round crater, even though it is a very slanted impact. So, secondary craters, another class of craters that are created by the impact of ejecta thrown by a crater's explosive formation. Now, secondary craters are shallow and generally small because the impact speed of the projectile cannot exceed the 2.4 kilometer per second escape velocity of the moon. If a projectile is heaved out of a crater impact at a higher velocity, it goes into orbit around the sun. Now, a majority of smaller craters, smaller than 20 kilometers, are believed to be secondary craters. Secondary craters can appear hundreds of kilometers from the primary impact, so sometimes it's tough to associate a secondary particular crater as being a secondary from a certain primary impact. But in the case of like Copernicus here, we can clearly see radial chains of secondary craters radiating out, or these ropey strands of multiple impacts thrown out from the Copernicus impact. Now, there are elongated craters. However, in the case of Haensel, it is two overlapping round craters, and our slanted perspective kind of turns them into a peanut shape. The same with Rhea E, multiple overlapping impacts. However, Schiller, that's another case. Down in the southwestern part of the moon, Schiller is a single oblique impact. Now, to show you the size of this, Schiller is 170 kilometers long. I'm not going to say wide, long, but if you translate that 170 kilometer length into a circular crater, Schiller would be one of the 10 largest craters on the moon. And not all craters are round. Here we've got Anaximander A and B, and kind of pivoting off of Carpenter crater, creating this Valentine, inverted Valentine. My lunar good luck charm, Meton, looks like a four-leaf clover. 4 overlapping craters whose interior were filled in with debris from the Imbrium Basin impact and obliterated the inner walls, but the apparition of a four-leaf clover remains. Agrippa and Godin, Agrippa on top, kind of bullet-shaped, Godin on the bottom, shaped like a bell. Now there's pentagon-shaped craters, hexagon-shaped craters. There's even square craters. I'll show you a square crater in a little while. Another class of craters are called floor-fractured craters. These started off as the classic complex crater, central peak, collapsed terrace wall, so forth. But volcanic pressure from below forced lavas up from under the crater, sometimes flooding the interior of the crater, almost always pushing the crater floor upward, elevating it, and in the process creating these rill structures that crisscross the interior. The most famous one, Gassendi, I call it my oatmeal cookie crater because it looks almost like an oatmeal cookie out of the oven. Posidonius up on Mars Serenitatis, and then Atlas crater, even further north from Posidonius, all prime examples of floor fractured craters. Ghost craters. Now, these are craters that existed prior to the Mare forming volcanic flows 3 billion years ago. the large basins were also impacted by subsequent impacts. Craters formed within these basins on the basin floor, but then lava flows buried them. And many of them are now totally unseen, but the larger ones are large enough that the crown of the crater will protrude above the Mare surface and protrude above the lava flooding. Lamont crater on the lower left is an example of actually a ghost basin. Lamont is not 300 kilometers in diameter, but the outer impact ring is another indicative feature that allows us to classify something as a basin. And this Lamont clearly is a double-ringed feature that has been buried under lavas, and the wrinkle ridges buckle up over the rim of it and reveal its location. This is just slightly north of the Apollo 11 landing site. And then up near Copernicus, almost hidden by Copernicus secondary craters, we see the ring of Stadius just barely protruding above the basalt. And then the famous Flamsteed P, the Flamsteed Ring, 100 kilometers in diameter, down on southern Oceanus Procellarum. Crater chains are another variation. To explain a crater chain, think back about 30 years to those glory years of comet Shoemaker-Levy 9 impacting Jupiter. The comet was broken up by Jupiter's gravity into multiple fragments. The same thing happened in the Earth-Moon system, early Earth-Moon system, billions of years ago. Crumbly asteroids, light, fluffy comets broke up and sequentially impacted the moon in a chain of impacts. Catena-Muller, Catena-Davy, very near the visible center of the moon. Catena-Abulfeda, just south of the Apollo 16 landing site, over on the eastern side of the moon. Abulfeda is almost 200 kilometers long, a significant feature. Now, wrinkle ridges are another feature on the moon, known by the scientific name of dorsum or dorsa in the plural. These are folds on Mare surfaces where sheets of basalt have crushed together and buckled up into a lengthy ridge that rarely exceeds several hundred meters in elevation, but can extend for hundreds of kilometers in length. Typically, if they're named at all, wrinkle ridges are named after Earth scientists, and the most popular wrinkle ridge in the illustration is the Serpentine Ridge on eastern Mare Serenitatis. And the Serpentine is the combined lengths of Dorsa Smirnov and Dorsa Lister that meander along the eastern shoreline of Mare Serenitatis for hundreds of kilometers. Other wrinkle ridges, here we see Sinus Iridum up on the northwestern shore of Mare Imbrium. The wrinkle ridges within it look like frozen ocean waves washing into the horseshoe bay of Sinus Iridum, and then arcing down toward the lower left. We see other wrinkle ridges, including Dorsum Heim. Yet another geologic feature on the moon are rilles. Now, these are scientifically known as rima or rimae in plural, and they are grooves or channels on the moon that are appreciably longer than they are wide. Now, these are formed by 3 different processes, but they are all volcanic in origin. So let's take a peek. Now, straight rilles were formed by the slumping of land between 2 parallel faults. The crust is split apart by a volcanic dike, which is a vertical sheet of magma that pushed up from the moon's molten core, but did not breach the surface as a volcanic eruption. Examples, Rima Hesiodus, down on the southwestern part of the moon, and over near the western limb, Ramus or Salus. These extend for hundreds of kilometers and were created by the splitting of the surface by a volcanic dike, and the land collapsed between these 2 faults. Arcuate, or curved rilles, are created by the stretching of land near the edge of a maria. What happens here is the mass of the Mare basalt in the basin slumps toward the middle of the basin. And as it does that, it pulls the land near the edge and stretches open these rilles. In this case, Ramahipolis looks like a gigantic cat scratch arcing around the eastern side of Mare Humorum. And one of the most famous rilles on the moon was the Apollo 15 landing site, Hadley Rill. I don't know how many of you were around or aware of space activities back then, but it was the last lunar mission that was broadcast live in its entirety for 3 days. Everybody on Earth was able to follow along with Dave Scott and Jim Irwin as they explored the Hadley Rill area. And sinuous rills like this are created by the flowing streams of lava, much like channels are cut in the Earth by flowing water. The flowing lava also erodes a channel. Now, scarps on the moon, scientifically known as rupes, are formed by two different processes. Some scarps, such as the Rupus altai in the illustration, are the surviving rim of an impact basin. In this case, Rupus altai is the last surviving segment of the outer Nectarius basin impact ring. The rest of it has been obliterated by subsequent impacts. Now, other scarps are created by the slumping of land on one side of a fault, such as Rupus Cauchy, the lower one of these two features, bracketing a Cauchy crater. The upper one is a rill. The bottom one is a Rupus, or a scarp, where the land is slumping down instead of collapsing between two faults. Now, the most famous of the scarps on the moon, of course, is Straight Wall, Rupus recta. This quickly becomes a lunar favorite of newcomers to the moon as well as seasoned observers. Now, at sunrise, the cliff casts a shadow. At sunset, the sun is on the opposite side, brightly illuminates the slopes and makes it appear as a white line. Now, past volcanic activity on the moon is evident in the form of pyroclastic deposits, sinuous rills, ash deposits around cinder cones, and volcanic domes. So let's look at some of these volcanic features. One of the largest is the Aristarchus Plateau on northern Oceanus Procellarum. This basically rectangular plateau is built up by volcanic eruptions, and evidence of that can be seen in Schroeder's Valley. The sinuous rill running through the middle of it once flowed millions of tons of molten lava onto Oceanus Procellarum. Right near the center of the moon is a heart-shaped pyroclastic deposit covering these hills north of Ramahygenus, and And the hills are basically heart-shaped, as you can follow my cursor. So I call this area the heart of the moon. Now, ash deposits around cinder cones can be seen inside of Alphonsus crater, primarily near the full moon, when the contrast is greatest in the crater between the dark and the light areas. Now look at the 9 o'clock, 3 o'clock, 5:30 positions. You can see these dark, smudgy deposits of ash around these ancient volcanic cinder cones. And this past volcanic activity is one of the reasons why the Ranger 9 spacecraft back in 1975 was deliberately targeted toward Alphonsus to try and get a handle on some of this volcanic activity. Unfortunately, Ranger 9 didn't see any volcanic activity or evidence of recent volcanic activity, but nonetheless, it was a fun ride because Ranger 7, as Ranger 9 broadcast their images live, they were rebroadcast live over a morning television broadcast, and the entire country could follow with Ranger 9 as it drilled down toward Alphonsus and finally impacted the crater. Other volcanic activity evident, the Marius Hills, a collection of around 250 volcanic domes and cinder cones over on the middle of Oceanus Procellarum, and then further north from the Marius Hills, this bubble-like swelling, about 60 kilometers in diameter, Mons Rumker, elevates up about a kilometer, and it's got little volcanic domes on top of it. So let's put some of the pieces together and start looking at some favorite targets that people like to observe on the moon through a modest telescope. I mentioned Plato crater earlier, very unique because it's completely filled with basalt. We don't see a central peak. We don't see collapsed terrace walls. It just does not look like other craters. Now, I had mentioned well, it's north of Mare Imbrium, like I said, between Imbrium and Fagoris. But I had mentioned square craters at one time, so let's go far enough here. W Bond, very square in its appearance, almost looks like built up for rampart fortifications and a fort in the middle of the desert. Very distinctly square-shaped crater. And getting closer to Tycho now, excuse me, Plato. Now we're beginning to pick up the tiny little craterlets within it, and of course the Alpine Valley. Boy, is my thing not working. There we go. The Alpine Valley through the Alps Mountains. South of Plato, there's some mountain peaks protruding from Mare Imbrium. These become very beloved to observers. Mons Pico, Mons Piton, and then just below it, look at the curious hammer-shaped structure. I call it Thor's hammer. And zeroing in even closer, now we're beginning to see in detail these craterlets within Plato and the central rill, sinuous rill running down the middle of the Alpine Valley. If you can see that in your telescope, we'll cherish it because you have got some really good seeing going on that night. Tycho crater stands in the middle of the southern highlands of the moon. Tycho is one of the youngest large craters on the moon. We believe it's about 104 million years old, which means it formed at the height of the dinosaur era. The formation of Tycho, the flash of its formation, probably startled many a T-Rex here on Earth. But an interesting thing is its location. Tycho, very, very young, is surrounded by all these much older craters, Longomontanus, Clavius, and others that are up to 40 times older than Tycho. These are Longomontanus, Clavius, these others are among the youngest, the oldest craters on the moon, survivors from way back pre-Nectarian era. Come on, go forward. Here we got a close-up of Tycho. And Tycho is famous for its broad ray patterns, spreads almost all the way across the southern hemisphere of the moon. But I like to look at Tycho under low sun elevation, high magnification. Look around the crater, all the hundreds and hundreds of tiny, tiny little pits everywhere, all around Tycho. These are secondary craters created by the debris flung out from Tycho. And it just completely altered the landscape. And you can see this in a telescope at low sun elevation when the shadows are filling these tiny little craters. And even at higher elevation, you can still see how coarse and almost pitted and rusted looking the surrounding territory is with all these Tycho secondaries. Copernicus. The ancients, not ancients, but the first telescopic observers 400 years ago, referred to Copernicus as the monarch of the moon because of its massive ray system, which covers the entire field of view here. I like to think of the ray pattern around Copernicus. It's like if somebody had an accident at a grocery store parking lot, and they're strolling across the HEB parking lot and dropped a sack of flour, and it just splattered onto the black asphalt and sprayed out in all directions. And that's what Tycho crater looks like to me. Oh, I mean Copernicus, excuse me. And even at the low sun elevations where the rays aren't that easily seen, the Copernicus is still spectacular. Just south of Mariam Rim, Eratosthenes crater at the base of the Apennine Mountains. The Apennines seem to point like a finger directly at Copernicus crater. Just south of the Carpathian Mountains, we see the swirls of secondary craters thrown out by Copernicus. Mare Insularum, just west of Copernicus. I had mentioned that one of the lunar seas had been named after I moved into the house I'm living in right now, 1976. So Mare Insularum gained its name well into the space age. And they call it Mare Insularum, the Sea of Islands, because as the sunrise view shows, the dozens of peaks protruding through the basalt makes it look like islands in a sea. Then just for artistic effect, we threw in Reinhold crater down at the bottom. So, wrapping up the sentimental lunar favorites, straight wall again. Like I said, it quickly becomes a lunar favorite for both novice and experienced observer. Where is my pointer? There we go. On western Mare Nubium, just below Arzachel crater, very near the center of the moon. Thebat crater lies just east of it. And because Straight Wall lies within this gigantic ghost crater formed, you see the horseshoe bay here of the land side of it, but covered by Mare Nubium basalts. The western rim of the crater, only visible by the wrinkle ridges. This gigantic crater has no name, and it's one of the largest on the moon. So by convention, we unofficially call it Ancient Thebat, named after the Thebat crater on its eastern rim. Now consider Straight Wall at sunset. Imagine if you would, you're an astronaut 50 years in the future. There's a science base there, and you're out after at sundown, enjoying the view. Everybody enjoys a sunset on the Earth, watching the sun go down to the horizon and slowly slip below the horizon. Now on Earth, as soon as the sun touches the horizon, you can almost set your watch 2 minutes, and the sun is gone. Now, bear in mind, the moon rotates much more slowly. Sunset on the moon takes an hour because the moon rotates about once a month. So standing on the rim of Straight Wall, watching the shadows approach across Mare Nubium as the sun goes down, have a long time to contemplate the beauties of the universe. It's going to take an hour for that sundown. Now, we'll wrap this up with a look at not all of these, but some of these nicknamed features on the moon. Now, just as we identify many deep sky objects by a nickname, we don't say NGC what the heck. When we're talking about the North American Nebula, we say the North American Nebula, and everybody knows what it is. Probably half the people in the room don't know NGC 7000 is the North American Nebula, but everybody knows what it is when you say the name. Now, there's things on the moon with similar things. So some unnamed features on the moon have nicknames. So we'll look at a couple of those just to get you up to speed. I had mentioned my lunar good luck charm, the four-leaf clover pattern created by the overlapping forms of Meton and Meton C, D, and E craters. And another nicknamed feature. We were looking at the straight wall earlier, but on the western side of it, where not straight wall, Alpine Valley, where it empties out onto Oceanus Procellarum, there are two massifs, almost 2 kilometers high on either side of it, where the Alpine Valley chokes down to a little canyon about 200 yards in diameter. Those features have no name, but Chuck Wood unofficially calls them the Guardians, and that works for me. Thor's Hammer, the T-shaped mountain ridge south of Plato crater. It reminds me very much of Mjolnir, the magical hammer wielded by the Norse god Thor. So I call it Thor's Hammer, and hopefully that name will stick. Now, whoever called this volcanic dome on western Mars Serenitatis the Valentine Dome, I'm not sure why. It looks round to me. I do not see a Valentine in this, but it's been called the Valentine Dome so long that that's what we call it. Or whether it's a Valentine or not, it is the Valentine Dome. And Cobra Head, the 4 kilometer diameter volcanic pit that once was the source of the lavas that flowed down Schroeder's Valley onto Oceanus Procellarum. And the heart of the moon. You see the distinct heart shape of this area darkened by ash deposits blown out by the volcanic vits along the Hyginus Rill. And my lunar spider, Lamont. Lamont, the ghost crater, but there's radial wrinkle ridges going north and south that make it look very much like a giant lunar spider. And just for reference, the Apollo 11 landing site right around here. And the ghosts of Procellarum, southern Oceanus Procellarum, is rich with ghost craters where the crowns are just protruding above the Mare basalts. Here we see Flamsteed P and Witchman R and various other small ghost craters, just arcs of them protruding above the Horseshoe Bay of Latrone. This whole collective area, I call it the ghosts of Procellarum. Now the railroad tracks are the twin parallel ray streamers extending northwest from Tycho crater. Now this is a bit of a mystery. Now crater rays all converge at the middle of the crater where the explosion occurred that created the crater. But look at the railroad tracks. They're almost tangential to the rim of Tycho crater. And if you can figure out why, your name is going to be on a research paper. The golden handle, the rim of the Jura Mountains, which form the arc around Sinus Iridum up on northwestern Mare Imbrium. At sunrise, the rim of the mountains is struck by sunlight before the interior of the Horseshoe Bay of Iridum is illuminated. So this golden handle floats in space. And the Marius Hills and the Tadpole. And spoken about the volcanic Marius Hills earlier, that there is no official name for this cluster of volcanic mounds. It's been called the Marius Hills ever since, I don't know, named after Marius crater right here, of course. But it's a nickname that is just stuck so well that it's even cited in research material. And then, of course, the tadpole, Rainer Gamma, this enigmatic white albedo feature. It's not a depression, it's not a mountain, it's just a light-colored region on the moon, and it's shaped very much like a tadpole. So, the fireman's hat over nearby oatmeal cookie crater Gassendi. It's upside down, but this volcanic mound near Gassendi crater resembles an inverted fireman's helmet. And we'll wrap this up. I think this is the last one. Huygens sword and stag's horn. Rupus recta, the straight wall, of course, is the long black line, but there's some unnamed hills at the base of it, and then Stag's Horn, this partial arc of a ghost crater. In your imagination, straight wall is the blade of a sword. These hills are the sword guard, and Stag's Horn is the sword handle. And we call it Huygens sword because Christian Huygens, back in the 17th century, was the first to really observe this area with the crude telescopes of the time. So, yes, that was my last one. So we'll conclude here by saying the moon is ever changing, as evidenced by the sequence of pictures at the bottom. We see the shadow within Ptolemaeus crater getting shorter and shorter and shorter. This occurred only within a 2-hour time frame. So the moon changes before your very eyes in one night. Now the moon's phases grow and shrink day by day. The shadows change hour by hour. And the moon is a geologic wonderland. The moon is accessible from your backyard. The moon laughs at light pollution. So there's much to love on the moon. And I invite you to come join me on my playground and enjoy the moon. So thank you for your attention. And I'm going to stop sharing and address any questions if anybody's still awake.
Yeah. Thank you very much, Robert. It was very informative. We do have a number of questions. First one from Dan Roy. You want to come off, make sure you're off mute and ask your question.
Yes, first, thank you so much. It was one of the most spectacular and rich presentations that I remember in a long time. Thank you so much for this.
Thank you very much.
I learned a lot from you, including annotating my slides, and as you can hear, my version of English, I think I will remember that lesson. One more thing I have learned from you. Now, we have about the same age. And I remember back in Apollo, they said, oh, the moon is dry as bone dry. Mm-hmm. And now we understand we could have swimming pools up there. Now, how much water do we know there is really out there?
The answer to that has not yet been determined. Now, there's been various missions that were supposed to explore that. The Lunar Viper, for one thing, put together, ready to fly, ready to go to the South Pole, rove around, prospect through the regolith, analyzing exactly how many water molecules are there in there, ready to go. NASA decides, oh my gosh, this thing costs too much. We can't fly it at all. So now we're going to launch the rocket to the moon with nothing aboard it and leave the Viper on the ground. So that would have answered a lot of that question. There are several other missions ready to go that will drill into the surface and analyze the prospect for ice, but they're going to be doing it from a fixed location. Viper was going to do this as a rover and go over extended regions. So it was the most incredibly boneheaded cancellation I have ever seen. And I wrote an article about it in Astronomy magazine, and some of you may have seen it. But we have things in the pipeline that are going to answer those questions. Because right now it's all speculation. We've got remote sensing from lunar orbit showing us signatures of hydrogen, but until we get down there and actually scoop into it and see what is in the regolith, are there ice crystals in there? We're not going to know for positive. So it's an ongoing investigation.
Okay. Jonathan's got a number of questions for you, Robert. So hopefully, Jonathan, you want to come off mute and ask your questions.
Yeah, I'm here. Thanks for the presentation. Yeah, I mean, I love astronomy, so there's plenty of stuff to ask. But I think with the water, okay, so I saw an astronomy show. They said most of the water on Earth was created during the late heavy bombardment, where meteors came down, and meteors tend to be about 20% water. So they say a lot of that water boiled off and formed the oceans. I guess one question is, are a lot of those meteors hit the moon? I mean, is that water there, or
Well, the import of water from comets and meteor origins. I'm not going to deny that it didn't happen, but the environment of the moon is such: no atmosphere, low gravity, exposure to the solar wind, because the very quickly the moon moved away from the Earth and got away from our magnetic field. So the solar wind is very efficient at stripping that stuff away. So the lunar environment is not very conducive for keeping large amounts of water. That's why we're very hopeful that these cold traps at the poles have frozen it into the regolith. There's mechanisms where the solar wind can impact the lunar surface directly, and hydrogen atoms in the solar wind react with oxygen atoms and oxides in the lunar minerals and create water literally molecule by molecule. And then the solar wind and various other forces migrate these molecules over long periods of time toward the poles, where they fall into these cold traps. And we're hoping that a significant amount of it has accumulated over literally billions of years. But still, like I said, until we get up there and actually dig into it and do an in situ analysis, this is all theory augmented by remote sensing. So exactly how much water the moon got early on, how much it kept, how much it has now, it's still an open question. It's one of the drivers of the Artemis program to go to the South Pole instead of more geologically interesting regions closer to the equators. The potentiality of water to make not only water for human survival, but to make oxygen, to make hydrogen and oxygen rocket fuel. So if the water is a viable resource on the moon, it's a total game changer. So that's why Artemis is concentrating on the South Pole. So it's going to be a bad day indeed if we get up there and find that there's just crumbs and drops instead of the bucketfuls like we really hope. But until we get up there and actually dig around and analyze on the surface, we're just not going to know. So it's one of the exciting things we're looking forward to in the next year or two, as these missions, both American and international missions, zero in on this.
With Mare, I thought, was it a combination? Some people think it was the heat of the Earth at the time. The Earth was extremely hot.
Well, the Earth underwent melting just like the Moon did, and the Moon there still has a molten core.
But was it a combination of the gravity of the Earth pulling on the lava and the heat that created the the Mare just facing us, or is it
volcanism on the Moon? The early gravitational tides of the Moon being much closer to the Earth had something to do with that. Yes, the heat of accretion impacts. The heat from internal radioactive elements. There are a number of heat sources that can melt the interior of the Moon. I don't think there's going to be enough radioactive elements on the Moon to do that solely by the decay of radioactivity. But in the early Moon, tidal effects from the Earth certainly played a major role in squeezing and squishing the Moon and heating it up. And the effect of Earth's magnetic field on the Moon also plays into this, because once the Moon receded away from us, it had to rely on its own internal magnetic field to not necessarily rely on it for volcanism, but the presence of it would indicate the potentiality for volcanism, because in order for a planet to have a magnetic field, the Moon being a planet, you need to have a liquid core of conductive material primarily iron, and a heat source that will convect this material in order to sustain a magnetic field. Now, if the moon possessed a magnetic field even up through middle age 2 billion years ago, like this latest results from the Chang'e 5 mission suggest, that means there could be, excuse me, could have been quite a bit of volcanic activity on the moon in its midlife. Now we've already established by other analysis of return samples from northern Oceanus Procellarum that volcanic activity on the moon occurred as little as 125 million years ago. So now we have evidences that the moon was volcanically active essentially its entire lifetime. But we don't see active volcanism now. But still, 125 million years ago is geologically very recent when you're talking about a body that's 4.5 billion years old. So,
yeah, would the magnetic field of the moon be able to tell us about the time when the mare were forming? And
well, we have a good idea when the mare formed just by the geologic record of it. The magnetic field didn't have anything to do specifically with the mare formation. Mare formation was the low-lying basins simply flooded because there was a lengthy periods of volcanism. The mare didn't form overnight. It took darn near 1 billion years for them to form layer by layer of volcanic eruption, several feet deep, followed by another volcanic eruption a billion years later, another several feet deep. We can see evidences of these layers by looking at some of the younger craters on the moon that haven't been modified by subsequent impacts or erosive effects of lengthy exposure to the solar wind. And we can see in the crater walls these layering effect of volcanism, where a basalt layer was laid down, and above it a breccia layer where the basalt was beginning to be broken up by meteorite impacts, and then another solid basalt layer and another layer of breccia. There's evidences of this type of activity all over the moon where there's maria. So it's not a fast process to create a maria. It's literally a billion-year process. And the volcanism continued on after that, but not at such a fierce rate. And you can visually see on the moon regions like around Lichtenberg crater upon northwestern Procellarum. Lichtenberg is a rayed crater, meaning it's going to be less than 1 billion years old. Yet the southern part of it, the ray structure has been obliterated by a lava flow. So clear, direct telescopic evidence of late-stage volcanism. So the evidences are there that volcanism on the moon was a much more prolonged process than we thought just a few years ago.
They think a good portion. Oh, go ahead. Yeah, sorry, I don't want to ask too many questions.
I was going to say thank you, Robert. If we could shift gears a little bit, I think Matt and Erica have a question for you about photography.
Oh, okay.
That's a deep subject, I know, but maybe you could just touch real quick on some resources for them. Matt, you want to come off mute?
Yeah, sure. Yeah. So, yeah, you actually already asked the question. So, yeah, we were really impressed by your images, Robert, and yeah, usually we try to avoid the moon. But now after today, we are so inspired that we would like to capture images. Can you talk a little bit about your setup, your equipment, your best practices?
Well, I go at it rather heavy for extreme detail. I use a planetary camera. Currently, I use one of the QHY planetary cameras, a little 1.25" cameras that slip right into your eyepiece holder. And these produce a video stream that you capture. And typically I capture about 5,000 frames. It takes about 2 minutes because it operates at about 60 frames per second. And then run that through a software called AutoStackert. It's a freeware that sorts through all of these 5,000 frames. And you can tell it select like the best 10%, which is still 500 frames, and it will sort through these best images and create a single TIFF image out of all of these. So you end up, you start off with something like 11.5 gigabytes of video data, and the crunches and rattles and rolls on it, and spits out one single picture, which then I import into Photoshop, because the stacking process often introduces artifacts, particularly small craters. Will have an artificial central peak in them. Small craters do not have central peaks, so you got to Photoshop those out. Dark areas after the stacking process sometimes have smudgy gray regions in them, particularly around the corners of a dark area. I call them bathtub rings, and those have got to be eliminated, because shadows on the moon are dark. They're not gray, or at least from Earth. Our cameras are not sensitive enough to see the interior of a shadowed crater by reflected sunlight. So shadows on the moon are black. We need to make the images look real. So I remember one time, Tony Hallis, famous deep sky astrophotographer, told me that it often took him longer to process the image than it did to take the image. And of course, deep sky, you can be exposing for hours. And it's the same with the moon. Getting rid of the detail that is not real and enhancing the detail that is. It's an art that you have to learn what is real and not real on the moon, and work with it until you have a picture that looks like it was snapped by an astronaut from orbit. But nowadays, we've got a very simple way to bypass all of that. If you're a rookie just jumping in and you want to have results that you can be proud of, I say whip out your cell phone and get yourself a something like the Celestron XYZ cell phone adapter that will clamp the camera to the eyepiece. And I recommend the XYZ not because I work for Celestron, but because it's the only one I know of that is adjustable in all three axes: left, right, up, down, and in and out. The in and out is important because you have to hit the exit pupil of the eyepiece. Otherwise, your image is vignetted. You can have a dark shadow in the middle, or you can be looking through a porthole instead of seeing the entire image. And these cell phone images that people are getting nowadays just blow away everything I did for about 50 years when I was shooting the moon with film. So they're just a person with their first shot through a cell phone outstrips what we've done for decades. So that's the simplest way to do it. But if you want to torture yourself, well, dive in deep and get one of these planetary cameras and learn all the softwares and explore the moon to know what's real, what's not real, and process the images accordingly.
Thanks so much. One kind of related question: are you using like a special filter to only have
with the cell phone camera? You really don't need one, but the planetary cameras, they are very sensitive to infrared as well as visual light. So yes, I do use an infrared block filter because the infrared focuses at a different point than the visible light. So it will create a fuzzy image in addition to the in focus visual light image. So we've got to block that out, get rid of it. On the other hand, I go the other way sometimes. I use an infrared pass filter that is opaque to visible light. And that is useful when I'm trying to image the moon in broad daylight. Sometimes the very crescent phases, I can't get to them because they're so close to the horizon that they're behind my neighbor's trees. But if I shoot it up higher in the sky, it's daylight. So I use the infrared pass filter and block out the visible light, and I get a working picture.
Brilliant. Thank you. Thanks.
You bet.
Finally, Bill Spizzeri, you want to come off mute and ask your question?
Yes, Robert, thanks for a great presentation. There's a lot of data there, a lot of information.
Well, just buy my book and you'll get it all.
Well, thank you. Thank you. I appreciate that. Early on in your presentation, I think I'm correct that you mentioned the concept of plate tectonics. I didn't know that there was any visible on the moon. Can you tell me where we see plate tectonics?
No, the plate tectonics I was referring to is how the Earth is altered. I was referring to that in the formation of lunar mountains, saying Earth's mountains are significantly altered by plate tectonics, erosion, weather, oceans, whereas on the moon, they're the rims of basins that are frozen in time. There is no plate tectonics on the moon. I was referring to how the Earth is modified. I'm sorry if that didn't quite clarify that. Maybe I spoke too quickly, but no plate tectonics on the moon.
Okay, great. Thank you.
You bet.
All right. Thank you very much, Robert. It was a very edifying presentation. I think everybody will agree. There was something for everybody in this in this presentation, and we thank you very much.
I'm glad to hear that. Like I said, I wish I could have been in Houston to present it in person and visit with my friends, but life sometimes gives us circumstances where that's not possible anymore. But I am grateful for being able to be with you all anyway. So again, appreciate the opportunity, and it's been fun.